Okay, welcome to GADAPS. So today we have Anita Rojas, who is going to talk about period matrices. Anita, please.
Okay, thank you very much. Thank you for the invitation. I will talk about three methods we have been developing through the years, but now it is more or less rounded. And for that, first, I am going to give a brief introduction about the ingredients and why we wanted to compute period matrices of abelian varieties and which information can be extracted from there. So let's begin with a quick introduction. So the first step in this or towards this abelian varieties stuff is the complex tori of complex dimension 1, which is the following manifold. So let's take a complex number in the upper half plane and build this lattice, the integral combinations of 1 and tau. And that gives us a lattice, a discrete subgroup of maximal rank in the complex space. And we take the quotient, and that gives us a complex torus, something that looks like that. I am sure that you are familiarized with that. So the lattice sort of give us a region, a partition of the complex plane, and then you have to identify sides, and then you have that shape. Topologically, it's a compact topological space, and two of them are going to be equivalent or isomorphic if and only if the tau you use to make the lattice are related in this way, where that is an integral matrix with determinant 1 or in an invertible integral matrix. Okay, so the thing is that you have the first moduli space in sort of an analytic way. You have to take the upper half plane where these taus are taken, and two taus are going to be defining the same complex tori if and only if they are related in this way I wrote there. And so you have to take the action of this group in the upper half space, and the quotient gives you the modular space of this complex tori of dimension 1. And it is known that a fundamental region for the action of this group is this one. And you have these identifications given by the corresponding elements. For instance, here is that, and here you got that one. And that is the model, analytic model for the modular space of complex tori. So that is the first step. Next step, we increase the dimension. And for that, we consider the Siegel upper half space, which is the space of matrices of G times G size with complex coefficient, which are symmetric, and its imaginary part is positive definite. That is sort of generalization of the upper half plane. This is going to be called a Riemann matrix. And with that matrix, you can form this matrix, which is of G rows and 2G columns with complex coefficients. G is a diagonal matrix, and the coefficient in the diagonal has this property. this condition. And with that matrix, you produce a lattice. Now inside C up to the G. And with that quotient, you produce a complex torus of dimension G now. So in the one-dimensional case, so P was 1 tau, okay? And tau was an element in the upper half plane, and we are generalizing that. So we have this complex torus of dimension G. Moreover, this complex torus has attached a non-degenerate alternating bilinear form, E, that takes integer values on the lattice, okay? And in this basis, E looks like that, okay? The pair T, E, is called a polarized abelian variety because we fixed a polarization. D is called the type of the polarization. And when D is the identity, we said that the abelian variety is principally polarized. And those are the objects that we are going to be studying here. So as we talk about isomorphism in the one-dimensional case, here we are going to repeat the same. So the first morphism between them we are going to be interested on are the isogenies. So two tori are called to be isogenous, or when you have a function, a morphism between them, which is surjective, holomorphic, with finite kernel. In that case, T1 and T2 have the same dimension, so G1 is equal to G2 in that case. In terms of basis, which is the way that we are going to be dealing with these objects, the isogeny is captured by a couple of matrices, A and R, where A is a G times G complex matrix, and R is 2G times G integral matrix, such that the period matrices of both tori are related like that. See, so let me put names here just to be. This is called period matrix, and this is called the Riemann matrix. Okay, and D is the matrix of the sort of polarization. See, you put D there. So a lot of information about the variety is captured in the period matrix. And when you have, when we say given a variety, we are saying that we have the period matrix of that variety. That's the way that we are going to be dealing with those varieties. So if you have two of these varieties, you and there is this relation among them, that means that you have an isogeny. Okay, and the kernel of the isogeny is captured in the determinant of that matrix, and so on. There is a lot of geometry of the isogeny captured in that relation, and this is called the Hurwitz equation for the isogeny. Okay. Moreover, this isogeny has a finite kernel, so it is an isomorphism if and only if both matrices are invertible and this matrix lives in the symplectic group. Okay. I am dealing here with principally polarized abelian varieties. I recall that that means that the D matrix is just the identity. Okay, so all the elementary divisors of the polarization are one. So again, we have
just a question for the isogeny. These D matrices are not necessarily the same, or you consider the same matrix, the polarization.
For the isogeny, yes, yeah. I am always being considering the the sort of, ¿cómo lo digo? Let me say better. So you can pull back the polarization of this one and pull back by the isogeny and produce a polarization there. So I am sort of respecting the polarization in that sense.
Okay.
Yeah. With that, you can take the we can build the moduli space in the analytic way again by taking this quotient in the same way we did it in the dimensional one case. So the moduli space of principally polarized abelian varieties is an analytic space of this dimension. Okay. So let's take a small detour, brief detour, because we want to relate this with Jacobian varieties. And for that, let me just recall some things that I believe you see in at least in Robert Auffart's talk. So let's take a Riemann surface. Briefly said that it's a topological space, a nice one, Hausdorff. We are going to be working with compact that locally looks like C. Okay, so it has an atlas that goes to C, but topologically it looks like a connected sum of one-dimensional complex torus. Okay, and when you have a Riemann surface, you have a notion of isomorphism between them, and you can build the moduli space of a compact Riemann surface of genus G, and you can inject that space into the moduli space of principally polarized abelian varieties by taking the so-called Jacobian variety of the Riemann surface. So, as I said, I watched Robert's talk, so I know he did that in more detail. The thing is that you can associate to a Riemann surface a complex torus in this way. You take the dual of the differentials and you mod by the natural injection of the first homological group there by taking integrals over the curves. And that gives you a complex torus, and moreover, you have an intersection product there that can be extended and gives you the depolarization, which is principal. Okay, so that gives us a principally polarized abelian variety associated to each Riemann surface. We have Torelli theorem, so that map is injective, and that part of the story. So why I am recalling this? Because inside the modular space of abelian varieties, we have a distinguished loci, which is the locus, which is the locus of Jacobian varieties, or the Torelli locus. And the dimension of Mg is 3G minus 3. And as soon as G is greater than 4, you have that this is a subspace of the other one. And that is where the Schottky problem arises. Okay, well, which abelian varieties are in the image of this map? Okay, we are not going to go to that way. We're going to go through a different path. So some definitions, because these are the kind of questions we are going to be addressing with this period matrix stuff. Okay, so an abelian variety is set simple if and only if the only subterrae that it has are the trivial ones. For instance, elliptic curves are the simplest abelian varieties, but you can have simple abelian varieties in higher dimension too. An abelian variety is said so simple, we like. An abelian variety is said completely decomposable. Some people said splits. If and only if it is isogenous to a product of elliptic curves. Okay. As a complex tora, not necessarily this good behavior of the polarization we were talking about before. Just as complex tori, we said that an abelian variety is completely decomposable if it is a product of elliptic curves. You don't need the polarization decomposed. And the other definition we are going to be interesting on is the concept of complex multiplication. So an abelian variety has complex multiplication. Well, a simple abelian variety has complex multiplication is and only if its endomorphism algebra over the rationals, tensor by the rationals, is a totally imaginary quadratic extension of a totally real field of degree the dimension of the variety over Q. So the thing is that you have Q here, and you have here something of degree G, which is a totally real field. Every embedding lives on the real. And then you have a 2 here, and you have the endomorphism, the variety, okay? So that is which is called also a CM field, okay? So that is the definition of complex multiplication for a simple abelian variety. And if the abelian variety is not simple, it is said of CM type if and only if it decomposes into simple factors with complex multiplication, okay? So that is our definition, I mean, not our, but one definition of CM type, okay? So if A is not simple, when you want it to be decomposed into simple factors, and each one of them has complex multiplication, okay? Those are the three properties that we want to explore for abelian varieties. So time, okay. So which questions are around these subjects? So in 1993, Ekedal and Serre asked about Jacobian varieties completely decomposable. So it is still unknown if there is a bound for the dimension of completely decomposable Jacobian varieties. Remember that that means that the Jacobian variety is a product of elliptic curves as a complex tori. Okay. It is still unknown if those kind of Jacobian varieties stop appearing in some high dimension. And another question, moreover, is if there is such a Jacobian variety for each dimension. And in the same work, they show this theorem, and you see there are some gaps there. So for instance, 30 was unknown if there were an abelian Jacobian variety, which is a product of elliptic curves. And there are some gaps there. They are known now as Ekedal and Serre gaps. There are several gaps that they ask if there were a completely decomposable Jacobian variety there. Moreover, they ask if they stopped. Yeah. And this is the higher dimension they found that there is a completely decomposable Jacobian variety. So that is a question that interests now. Another question is the so-called Colemans conjecture, given in 1987. And he asked if, given a dimension greater or equal than 4, if there is only finitely many non-singular projected curves such that its Jacobian variety is a CM. I mean, remember that that means that splits into simple factors, and each factor has complex multiplication. So it has an interesting property in its endomorphism algebra. It is still unknown if there are finitely many. It is known that it is false for genus at least 7, but it's unknown if there are infinitely many of such kind of Jacobian varieties in higher genus. Well, Bouville in 2014 was talking about complex multiplication, and he asked about examples of Jacobian varieties isomorphic to product of elliptic curves, so completely decomposable Jacobian varieties very strongly, because you want isomorphic, not just isogenous, and the elliptic curves having complex multiplication. He exhibit their examples up to dimension 10, but he asked if, and as far as I know, there are not many examples of that. Well, another question, the last couple of ones I'm going to show you is were asked about by Moonen and Oort in 2011, in a work of 2011, and their questions suggest that you have to think beyond group actions. They ask if it can be constructed a curve of genus at least 4, so a Jacobian of dimension at least 4, without automorphism, such that the Jacobian variety is of CM type. And another question in the same work is that if there is a positive dimensional subvariety of the Torelli, of the closure of the Torelli locus, intersecting the Torelli locus, such that the generic point is isogenous to a product of elliptic curves. So those are questions, as you can see, about the moduli space of abelian varieties, and you want to describe particular loci there. So let me finish this introduction with some fundamental theorems. So the fundamental decomposition theorem here is called the Poincaré reducibility theorem. Well, first, it says that if you have a principally polarized abelian varieties and a subtorus inside it, then it has a complement with respect to the polarization, okay, such that the intersection is finite. So the abelian variety will decompose always. In this case, we are, of course, in the analytic world, we are talking about complex abelian varieties. And well, this can be generalized to the so-called complete reducibility Poincaré theorem. And it says that if you have an abelian variety, so it has a polarization, there is an isogeny like that, where the factors are simple abelian varieties, not isogenous to each other. And moreover, this decomposition is unique up to rearrangement and isogenous. Okay, so this is the fundamental theorem of decomposition in this theory, you know. So those are the simple factors, and they are uniquely determined up to isogenous. So the goal is, well, considering what I am been talking, the question that I presented before, the goal here is to find this decomposition, because you can study the simple factors and see whether they have complex multiplication or not. And with that, you can determine whether A has complex multiplication or not. And if these factors have dimension 1, then that means that A is completely decomposable. So the aim is to find the Poincaré decomposition of a given abelian variety. And by given, I understand we have the period matrix of A. Okay. So just another tool. So with that goal in mind, to find the Poincaré decomposition, what do we have in hand? We have the so-called the group algebra decomposition due to Langevin Resillas in 2004. And it goes as follows. So when you have a group action on the abelian variety, it induces a morphism from the group algebra over the rationals to endomorphism of the variety tensor by Q. And with that, you can sort of transport or translate the known facts about this algebra, which is a semi-simple algebra, to the endomorphism algebra of the variety and to the variety itself. So first, you know that the semi-simple algebra decomposes into a product of simple algebras. And those algebras are generated by central idempotents in the group algebra. So you can take this decomposition through this morphism to a decomposition of the variety A. So once you have a variety with a group action, you can decompose it using the information about the group. Moreover, the decomposition of these are simple algebras. So the decomposition of the simple algebras into product of minimal left ideals, again, you can translate that decomposition to a decomposition of each one of these factors. Okay, so this is called the isotypical decomposition because all these factors has a group action. The group acts there. In fact, acts with the rational representation associated to these factors. So representation theory comes into the play here. And this decomposition is unique. The central idempotents are uniquely determined. So these are the image of each central idempotent, which can be built using representation theory. So this representation, decomposition is uniquely determined. And this other is not. So that's why I use the isotypical decomposition and a group algebra decomposition. It's kind of to say that this is not longer unique. You have several minimal left ideal decompositions for each simple algebra, but each one induces a decomposition of the abelian variety, and this is as far as you can get where we're using group actions. So these factors cannot be decomposed further using the information coming from the group, because you reach the point of minimal left ideals. Okay, but it doesn't mean that this is the Poincaré decomposition. Okay, these factors could be isogynous. These factors could be not simple, and so on. Okay, so that gives you a point, but you could need to go further. Okay. So immediate questions that are, of course, related with the main questions I presented at the beginning of the talk, but you get immediate questions when you see this group algebra decomposition. So are the factors simple? Under which condition they are simple? Okay, are they isogynous to each other? Under which conditions they are isogynous to each other? Because those questions would allow you to find the Poincaré decomposition of the variety. When we can go beyond the group algebra decomposition, because as I said, those factors are not simple. So how can I decompose them further? How to find the Poincaré decomposition from the group algebra decomposition? And before going to Poincaré decomposition, we could want to describe the dimensions of the factors, the induced polarizations on the factors, the endomorphism algebras of them, if they have complete multiplication or not, and so on. So from the group algebra decomposition, you can get some information of the variety A. For instance, we were able to improve the gaps of SER. Okay, that's to fill some gaps. So the ideas and approach of what I'm going to show you, and now we are sort of entering to a current work, is the following. So first idea is to go beyond the group algebra decomposition by studying the subvarieties there. So to find out whether they decompose further or not, to obtain the Poincaré decomposition from there, and so on. And for Jacobian varieties, we want to combine the group algebra decomposition with other tools to tackle questions about complex multiplication and completely decomposable varieties, and that's it. And for that, one tool is to describe the period matrix of abelian varieties with this kind of, when I'm saying interesting properties, I am saying the properties we are interested now. So just using the group algebra decomposition, we were able with Jennifer Paulus to fill some gaps of Ekdal and Serre, okay? So if you remember, the smallest gap in Ekdal and Serre's work was 30. And with group algebra decomposition, we were able to fill that gap. That means that we found a curve. We found a curve X of genus 30, such that it has a group acting there in a way that the Jacobian variety of this curve decomposes as a product of elliptic curves when you study the group algebra decomposition. Okay, so fortunately, in these cases, which are bold here, the dimension of the primitive factors, meaning the factors coming from the decomposition into minimal left ideals, have dimension 1. So we found the Poincaré, no, not the Poincaré, so we found the completely decomposable decomposition of that Jacobian variety. It is not the Poincaré decomposition because we were working just with the dimensions, and we don't know whether these factors are isogenous or not. So maybe this one is even like that, and we don't know, okay? Because we just know the dimension, not the type of that, the lattice of that elliptic curve. So that's, if you want to find the Poincaré decomposition, then you need to describe the period matrix of those elliptic curves, okay? But still, it's a nice result in the sense that we filled several Serre's gaps, and now the smallest gap still unknown is 38. So we don't know, nobody still knows if there is a completely decomposable Jacobian variety of dimension 38. Okay.
Anita, do you compute the curves as equation explicitly or give explicitly the period matrix? Which
Some
one?
of them, but in this work, we just we're focused on the dimensions. And but for some of them, we have explicitly the Riemann matrix. I will show you one example in genus 11. Okay, so now I am sort of finishing. I am going to, in the last part of the talk, I am going to explain to you 3 methods to compute the period matrix of an abelian variety, depending on the geometric information you have. And the idea is to combine these 3 methods to compute the period matrix of abelian varieties, and in that way to find out whether they have complex multiplication, whether they are completely decomposable, and so on. Okay. So the first method is when you have an endomorphism of an ambient abelian variety, and you have the period matrix of the ambient abelian variety. So this allows you to compute the period matrix of the image of the endomorphism. Okay, so every endomorphism defines the image of the endomorphism is a subvariety of A, and this method allows you to compute the period matrix of the subvariety defined by that endomorphism if you know the ambient abelian period matrix. Okay. So the input for this method is, another thing that it is useful about this method is that they can be programmed. We did that under Magma and Sage, and so you can actually compute the Riemann matrix. Of course, sometimes they have, big coefficients and you can't see a thing, but still you can compute them. So the input is the rational representation of the endomorphism. This is the matrix representing that endomorphism in the lattice of A. Okay, once you have a basis of A, which is symplectic, so where you have the polarization in the way that I show you. So JA is a matrix like that. Sorry, A. And you have that period matrix, and if you have that information, then you have a matrix capturing the basis of the lattice. H is the dimension of, I should have said that. So AF is the image of F and of dimension H. Okay. So with that information, you get a matrix of that size, which is in fact representing, it's the rational representation of the inclusion, of the embedding of the subvariety defined by the idempotent. With that, you can restrict the polarization of the ambient variety and find the type of the induced polarization in the subvariety. So you have one part, and then how you find the Riemann matrix of the subvariety, which is a matrix living in the Siegel upper half space of dimension H. And that is, the theorem says that it is the unique solution to that equation. Okay. So just from this information, you can figure it out how is the period matrix of the subvariety. Okay, so that is why I said when I like when you have when I say given A is because I have the period matrix. Okay, and with that you can do a lot of stuff. But sometimes you don't have the period matrix of the ambient variety. So in that case, we have a second method, which is when the subvariety in question has G action. Okay, that is the case, for instance, when you have the isotypical decomposition. Okay, when you have a central idempotent, in QG, the image of A of that central idempotent is G invariant. Okay, so there are several subvarieties that can be found once you have the variety with group action. There are several subvarieties fulfilling this property, having the action restricted to it. Okay, so in that case, you can also compute the Riemann matrix of the variety with G action, and this can be used for the full variety. So if A has G action, then you can use this theorem to find the period matrix of A. But sometimes it is not doable with the computer because it runs out of memory and this kind of constraints. So in that case, what we do is to compute the central idempotents and the Riemann matrices of the period matrices of the subvarieties. And in combination with the third method, you can recover the period matrix of the ambient variety. Okay, so this method can be used for A, but in many cases, you can't do it because of problems with the computer. So that's why a detour is to find the Riemann matrix of the subvarieties and then recover the ambient one. Okay, so so for this, you just need to have G action. You don't need a period matrix of anything. It's different from the first method that you need the period matrix of the ambient variety. So you have the symplectic representation of the action, and you have the polarization of the variety you want to study. Okay, and with that information, you can find the following things. So the output is, well, as before, you have, since you have that, you have the rational representation for the inclusion. You have the induced polarization in the subvariety, and then you can compute the restricted action to that subvariety. Okay, with that, see, is the unique matrix solving this equation, linear equation. All these are matrices, and with that, you have to study. You can get the period matrix of the subvariety which had this G action because it satisfies this relation. Okay, and that gives you, you know, well, the input is that what you computed in the first step. This matrix is a matrix with this shape, and with that matrix you ask for the fixed subvarieties by this action, and that gives you the Riemann matrix for that subvariety. Okay, so we have a method for image of idempotents once you know the ambient variety. If you don't know the ambient variety, but you know it has a group action, you can compute the Riemann matrix of subvarieties with that group action. And with that, the third method is that with that you can recover the Riemann matrix of the ambient variety. So if you have subvarieties decomposing a variety A, that means that A is isogynous to the product of that, and you know the period matrices of the pieces. So for instance, using the former method, and you have the rational representation of this isogeny. With that ingredients, you can recover the period matrix of the ambient variety in this way. Okay, so it comes from writing this the Hurwitz equation for this isogeny, and you know the pieces, and you can put everything together, and you recover the Riemann matrix of the ambient variety. Okay. So the idea is to use these three methods to study varieties to begin with group action. Okay, that's the starting point. But as I told you before, that doesn't give you the Poincaré decomposition of A, and sometimes A decomposes more than the thing that you know. So for instance, in that theorem I show you, let me recall here a while, this here. So the smallest gap is 38. We did that by studying all group acting in genus 38. And we compute the group algebra decomposition for that. So that means that if there is a completely decomposable Jacobian varieties here, you are not going to capture it by group action only, because we study every group acting there. So you have to go beyond the group action. But group action can be a starting point. So if you start with a curve of genus 38 and you decompose using group action its Jacobian variety, you will get some sort of big pieces which are not elliptic curves, but you can study them with these methods I told you here. Okay, that's the sort of the project. And for that, another brief detour is that with Robert Auffart and Herbert Lange, we developed a method to find out whether a variety is an abelian variety is has subvarieties or not, can be decomposed further if you have the period matrix of the Jacobian variety. Okay, I just put here the proposition for dimension 2 for surfaces because the equations are nicer if the dimension is bigger, the equations are difficult. But still, they could be programmed. We haven't done that. We did that for surfaces, but not for three-folds or higher dimensional varieties. But the thing is that if you know, well, here it should have said that here the Riemann matrix, because the period matrix, it's sort of like that. And then Z here, okay? That is the period matrix. This is the Riemann matrix. So it's a symmetric matrix with imaginary part positive definite. And A admits an elliptic curve because we are dealing with surface, if and only if there is a rational vector satisfying these equations. And the equations depends on the polarization and on the Riemann matrix, okay, of the surface. So if you have the Riemann matrix of a surface, you can say if that surface is simple or not. If there is a rational vector fulfilling these equations, then that means that you have an elliptic curve inside, so that surface decomposes further. Okay? So this is the kind of results that shows that to have the Riemann matrix or the period matrix of an abelian variety is useful, because you can study, for instance, if they decompose further. Okay, so to finish, in the last 5 minutes, I will show you an example, an application of all these things that I've been talking about. So let's start with that group. That is the label in the small group database, which is used in Magma and GAP and Sage and almost every mathematical software dealing with groups. So this is a group of order 96, and it is the 28th in the list of that database. So it acts on a curve M of genus 11 with that signature. That means that the initializers for this action are of order 24, 4, and 2. So with that information, we can compute the group algebra decomposition, and that it says that the Jacobian variety decomposes into these 5 factors. So 4 of them are elliptic curves, and 1 of them is an abelian surface to the square. Okay, and this is as far as you can go with group action. So that was an example of a curve that the Jacobian variety, we don't know if it is completely decomposable, okay, because it has a surface there. And we don't know if it has complex multiplication, because we just know the dimensions of the factors, okay? So, but we know that those factors are image of central idempotents. And moreover, those factors, the ones that are raised to the power, are image of primitive idempotents. So since we have the group and we have the signature and we have the group action, we can compute the central and primitive idempotents. And with that, we use the second method I show you, and we find out the period matrices of these factors, okay, of the primitive factors. So, for instance, E1 and E3 are isogenous to this elliptic curve, so it has complex multiplication. And E2 is isogenous to that elliptic curve, so again, it has complex multiplication, and E4 to that one, so also has complex multiplication. And we were able to determine that by computing the primitive idempotents and computing the period matrix using the second method, because we don't have the period matrix for the Jacobian, okay? It can be done with the computer. It runs out of memory. Moreover,
maybe this curve is once again the same question that I asked. Is given explicit as equation or
yes,
explicit?
That's a good question. No, we can't find equation yet. We would like to, but we don't have the equation. We just have its existence in the sense of group action. So since this group has the so-called a generating vector for this signature, that means by Riemann existence theorem that there is a curve of that genus with that action. Okay, so we can produce the Fuchsian polygon determine that curve. So as you know, we can take the unit disk and the Fuchsian group giving that curve, but we don't have the algebraic version of that. Yes, that's a good question, and that would be a good thing to have it. We have that in terms of Fuchsian groups. That is why everything what I'm talking about is it is using heavily that we are working in manifolds, in complex, in the analytic point of view. Yes, thanks. So we have that curve, as I said, in the sense of manifold and in the sense of Riemann surface. And we have the idempotence, so we can compute the image, and we don't have the Riemann matrix or the period matrix for the Jacobian, but we have in this point the period matrix of the primitive factors. And this is a surface, okay? But we have the Riemann matrix of the surface. So we're going to use on that this theorem, so I mean this proposition, this result, and we are going to study if this decomposes further. And that cannot be done without having the Riemann matrix, okay? So we are looking for a rational vector satisfying this system of equations, and it turns out that it has a solution. So we have that this surface decomposes further. So now, up to this point, we know that the Jacobian variety of that surface is Riemann surface is completely decomposable. Okay, but we have that all these elliptic curves have complex multiplication, and we know that this surface decomposes into two elliptic curves, but we don't know if they have elliptic complex multiplication or not. So for that, we sort of translate this tuple into idempotence and find the Riemann matrix of those images. And we found out that both of them are isogenous to that elliptic curve. So now we have in fact, we have the Poincaré decomposition of the Jacobian variety of that Riemann surface, and we can read more geometric information for that. So it is completely decomposable and it has complex multiplication. Unfortunately, this is an isogeny and not an isomorphism. We are not answering Boville's question by showing a Jacobian variety which is isomorphic to a product of elliptic curves. It is isogenous. But since we have everything explicitly, we can compute the kernel of that isogeny, and I don't remember, but we did it in some point. And so just to end, from this point, we could and we did recover the period matrix of that Jacobian variety, but I didn't put it here because it has sort of, well, beautiful or ugly, it depends on the point of view, but hard coefficients. It is in terms of the 20th root of unity and so on. I can show you if you want to see it, but it is not that beautiful. Yes. And that's it. A couple of references. That is where our work of decomposing, having the Riemann matrix is done. That is where Boville posed his question, Ekdan and Serre work, Lange and Resillas group action, theorem, Moonen and Oort, and our work with Jennifer Palos. Thank you very much.
Okay, thank you.
forgot how
Thank you.
I shared this. Well,
Anyway, any question? Eunice, if you want, you can stop the recording. I got